Hey, EP Chemisters, this is Mrs. Vandelay bringing you Blankwalle, Chapter 16, Part 5, Part 3, and it should be the end. This should be the last one for this section. So prompt number 24 says, calculate the molar solubility of cerium fluoride, CEF3, in each of the following cases of pure water. I really like this example as I really think it shows what happens when you have a common ion. So we'll work through these instances or these sections here, all right? So go ahead, you can do pure water. Just like what we've done before, there is no common ion in pure water. So go ahead and pause this, do it, and come back when you're done. All right, how'd you do? Well, this is what I came up with. So I have molar solubility in pure water of 7.4 times 10 to the negative 5th molarity, all right? Now the next one, you have a 0.2 molar of cerium trichloride, or cerium 3 chloride, I should say. So what's your common ion? Is it cerium or is it fluoride? Hopefully you realize it's cerium. So go ahead, and what changes here? What part of your ice table is going to be different here? You're not going to have a 0. So go ahead and pause this, do it, and when you're ready, come back. All right, how'd you do? So look here, your initial cerium is not 0, it's 0.2. Add x, so it's 0.20 plus x, all right? So here is this, here's my KSP. Actually, this got out of order, I apologize, there we go. And so this is your 27, or x cubed, times 0.2. Why did I do that? Because what happens here, we assume this is so small that it doesn't make any difference, okay? So now we have 8.0 times 10 to the negative 16th is equal to, should be 5.4. I just made a mistake, didn't I? This is going to be 5.4 times 10 to the, come here, which makes that number a little different, doesn't it? So 5.4 x cubed, and let me pause this and see what your actual answer is. All right, I think I fixed it now. So this is 27 times 0.2 is 5.4 equals x cubed. So this now is equal to 1. I divided both sides by 5.4. I get 1.5 times 10 to the negative 16th. I took the cube root of that, and now I get 5.3 times 10 to the negative 6. What does that do for you? Well, this is in pure water. This is with the common ion. Notice that you have less dissolving going on, all right? You have a lower concentration in solution. Well, what about the next one? And I kind of like this next one, all right? What's going to happen here? Where'd it go? There it is. What if I have a 0.2 molar of sodium fluoride? Fluoride now is my common ion. So go ahead and take a few moments out and work on this one. When you're done, come back. Hopefully I didn't make another mistake. All right, let's see how we did. Maybe I didn't make a mistake here. All right, so here we go. 0, I have a 0.2 molar here. Why isn't it like 0.6? Because there's only one fluoride here, okay? I only have one subscript, so it's still 0.20. And now what can we assume with this? That is small. So now we have x equals 0.2 cubed, all right, which is 0.008, okay? And so that x should not be there, or x cubed. There we go. I made a typo, but I didn't make a math mistake. So then we have 1 times 10 to the negative 13th is equal to x, and there we go. So that's your molar solubility. Whoa! Look at how little of the cerium dissolves now when you already have some sodium fluoride already in place. Very little bit. So again, if this goes up, I'm going to shift this direction, and I have less and less dissolve, okay? All right, so here we go. In which solution, whoops, is barium sulfate most soluble? You just saw the answer, didn't you? All right, so why don't you go ahead and figure this out. And when you're ready, I'll talk about the answer because I think you already saw it. All All right, hopefully you saw it was letter C. Why is it letter C? Why isn't it A or B? Well, because you have a common ion in here, right? You have a barium and barium sulfate, correct? So you're going to have a common ion. It's going to shift left. You're going to have least desirable there. Over here, I have a sodium sulfate. Sulfate is a common ion. All right, again, it's going to shift left. You're going to decrease the solubility. But in sodium nitrate, there is no common ion. It's just like putting it in water. There is nothing to shift left. So this one will be the most soluble. These two will be the least. They're going to be equal because you still have one barium and one sulfate, same molarities. All right, but this is going to have the most soluble because there is no common ion. Let's go to the next page. Okay, so this is huge. Okay, notice I have another star here. The effect of pH on solubility. All right, pH can affect the solubility of a compound in that solution. It can. Now, I don't know if you recall back in chapter 15 when we talked about strong bases. We said group 1 and group 2 are strong bases. But the problem with a lot of your group 2 hydroxide is that they don't dissolve, okay? They're considered insoluble. But I alluded to the fact back then that we could make them dissolve, all right? If we put them in a certain kind of solution, we can get these group 2 hydroxides to dissolve the entire way. All right, so what are we going to do? Well, it says if the pH is high, that means, bigger than 7 maybe, then hydroxide is high. And what does that mean? Well, let's look at Le Chatelier. If I have a lot of hydroxide, how will it shift? To the left, isn't it? All right, so it's going to shift to the left, and what would happen? It's going to decrease. Why? You're going to have fewer ions in solution if you shift it left, all right? Solubility goes down. We just did that. But what if the pH is low? Then you're going to have a lot of hydronium ions, and what's going to happen to the hydroxide concentration, all right? Let's think about that. If you have I'm going to get rid of the red now, all right? What happens if you have a lot of hydronium ions? Well, it's going to neutralize your hydroxides. I'll say it again. If you have a low pH with a lot of H pluses, it will neutralize your hydroxide, decreasing the amount of hydroxide. So how will it shift? It's going to shift it to the right, okay? And so once it decreases to the right, what's going to happen to the solubility? All right, it's going to increase. So it says more hydroxides will be created to make up for the hydroxides used to neutralize the additional H plus. All right, let me scooch this over here. So what's going to happen to the hydroxide? I'm answering that right now. Hydroxide will neutralize the H plus, therefore decreasing the OH minus. That's what this green arrow down here is doing. So if I put H plus into the solution, hydroxide is going to neutralize it. So now I've used it up, okay? So the hydroxide is going to go down, meaning it's going to shift to the right. So more of the magnesium hydroxide will dissolve, all right? So therefore, the hydroxide is going to increase again, all right? And solubility is going to go up, all right? And if I put it in some more acid, the same thing keeps going. Until when? Until you possibly dissolve the entire amount, okay? So that is huge. Why is this so important? Think of your antacids, okay? Most of the ingredients in your antacid is insoluble. But what is the purpose of your Tums or your Rolaids, all right? It's to neutralize your stomach acid. So it's not going to dissolve well in just plain old water, but it will dissolve very well in an acidic environment like your stomach. So it's going to neutralize that excess stomach acid, okay? And that is how you can make a strong base out of a group 2 ion, okay? So it says this: in general, the solubility of an ionic compound with strongly basic or weakly basic anions will increase with increasing acidity, all right? So if anion X is effective base, meaning HX is a weak acid, the salt MX will show increased solubility in acidic solutions, all right? So what are we talking about? The ones listed here, okay? These are more soluble in acidic water than in pure water, Okay, rainwater is naturally acidic, can dissolve your limestone. Okay, so let's check this next question out. Okay, so let me get it ready. All right, so it says the solubility of hydroxide precipitate is affected by the pH of a solution. Calculate the molar solubility of cadmium hydroxide in a pH 9.5 buffer. All right, so what am I going to do first? All right, well, I need to find out what my common ion is. So they told me that pH is 9.5. That means pOH is 4.5, right? So what does that mean now? Here is my hydroxide concentration is 10 to the negative 4.5. So then I could say my hydroxide is 3 times 10 to the negative 5th. So that is this value. Notice I'm not multiplying it by 2. All right, it's just the initial. What's the initial? Cadmium, oopsies, it's 0. So then I can do this, and now I can do this. I'm going to actually scooch it over so I have a little more room. Okay, so now what? All right, well, KSP is equal to, got to find where I put it here. Well, let's just go ahead and do this. Okay, I guess I didn't show my cadmium and then my hydroxide. And now what? Well, I'm going to assume X is small, 10 to the negative 14th, I sure hope so. All right, and so I am going to do something like this. So if I can, I'm going to cancel out this. All right, and like the sound effects. So then what do I get here? I get, oops, sorry about that. All right, I get X equals 3 times 10 to the negative 5th. Okay. Wow, that's like the initial POH, isn't it? Well, what happened here is that I actually calculated, oh, here is this. I did have it. I did actually calculate what's going on, and sadly, your 5% rule doesn't really work, does it? But you know what? If the 5% doesn't work, then I'm kind of in trouble because now you got a cube quadratic going, and I really didn't want to deal with this. All right, so I just kind of basically quit the problem here. I have to say that. There we go. So what happens now? What do you think is going to happen? If I have a common ion, the molar goes down. So what I did is I said, what about in a neutral solution? Because I gave up on that problem. I hate to say that. And I got the X is 1.8 times 10 to the negative 5th. So what's going to happen? I'm sure my X is going to be a smaller value than this. So you notice when I solve for X, it's a bigger value, but I think X needs to be smaller than that for the common ion to work. And so I'll just go with that. It's going to be a smaller value than 1.8 times 10 to the negative 5th. So that wasn't really a great problem. I apologize for that. So the next one was problem number 27. Determine whether each compound is more soluble in acidic solution than in a neutral. All right. So remember what we did in chapter 15? We were looking at if the salts were acid or bases. Okay. So this is what I did. Oh, this is the 5% rule. There we go. That goes up here. So BAF2, what do you notice? This is a group 1, group 2, neutral. F2 is the anion of a weak base, all right? So this is a weak base, and so if I put it in an acidic solution, my molar solubility is going to go up, all right? So I'm going to be more soluble. What about silver iodide, all right? Well, iodide is a neutral from the big 6, all right? But silver is not acidic, but you know, it doesn't make any difference if it's in it, if an acid's in an acid, it's not going to change anything. So you're not going to be any better off, all right? So calcium hydroxide is going to be greater because hydroxide is a strong base. And then finally, which of these are going to be more soluble in acid than in base, and why? Why don't you pause this and think about it and come back? I said iron 2 carbonate is more soluble. Why? Because I recognize this as a weak base. Bromide is an anion of a strong acid. It's neutral, so it's going to be more soluble in an acid. Okay? I promised you that was going to be the last one of section 16.5, and I'm true to my word, so this is it. So don't wait to be great, and we'll see you shortly, or see you next time with section 16.6. 6. All right, so don't wait to be great. Bye-bye.